Okay, thank you. So yeah, today I'm going to talk about what I did before I joined DDN MemCloud. So this is not what I'm currently doing, but this work is still work in progress and still continued by my colleagues, and it's about ad hoc file systems and also how we can use I/O frequency predictions and Lustre HSM to move data between two namespaces. So first we're going to start with some quick catch-up about ad hoc storage systems, and then we're going to start with these two topics. So let's start. So as the traditional sense, we have the parallel file system that the user is interacting with Slurm. They're defining the application scripts, and then the application runs on the parallel file system. And so this is the traditional way how they use it, and the way we looked at it is, well, the parallel file system and Lustre is a shared resource. So in this sense here, we have looked at the GPFS file system at Mare Nostrum 4, but we've also seen this in other sites that the I/O performance varies wildly for for identical workloads. So what you see here, every point here is a workload that was run over the course of the week, different times of the day. And you see that basically the performance read and write changes in orders of magnitudes. And so the applications, of course, they have different I/O performance, have different runtimes, and so on. And so our idea was, well, what can you do about it? And this is where the ad hoc storage system come into play. And at the basic form, an ad hoc file system is basically only a file system that is deployed ad hoc at the application nodes, and they use memory or node local storage that is already available and oftentimes actually not used, right? So improving data locality, do work where the data lives, minimize uncoordinated PFS usage. So you could imagine, instead of having small byte access to the PFS, you have this to the burst buffer file system, and then later move it out in a more sequential way. And so you see what we have here is that the user now has to do a little bit more, has to deploy this ad hoc file system, and then the application is using that, and we stage the data in and out, so input and output data. And so as an example here, and this is what we've developed at the University in Mainz, is the GeckoFS file system, which is a user space file system, first of all using system call interception, so not Fuse or a specific I/O library with a specific API, it's still POSIX. And the point here was the goal is it needs to be scalable, of course, and what we have seen is that the more nodes you have, so if you have twice the number of nodes, you get twice the number of performance. And because it's user space, basically people can deploy it without telling the HPC admins, because in the end it's just another application that they use. Fast deployment is also very important, right? We cannot wait for minutes until this is deployed, and we can deploy this thing with at 500 nodes in a couple of seconds, because we don't have any global locking mechanism in that file system. So it is still POSIX compliant, but because of that, there are also certain operations that are POSIX relaxed. And then hardware independence. Users should be able to use the paths that they're already having access to, the node local SSDs, and the network that is available. So I will not go too deep here into GeckoFS, but this is kind of the key points. We have several publications where I can read more, and also for the performance that we have. But for instance, we have already a couple of server nodes, millions of metadata operations, like stat and create and these things. And if we go back to the slides that I had before, with the variability, of course, because each application is using their own file system, you no longer have this variability, and you see basically linear scaling, right? And so this works well also for applications, but of course this really depends on, well, how many nodes you have, what kind of node local storage you have, how fast the parallel file system is the application I/O bound or not, right? These are all things that impact how useful an ad hoc storage system is, but in general, you see sometimes there's no benefit, but also sometimes it's like 40 times more bandwidth, or something like that. So, but ad hoc systems in real life, and this is where the Euro HPC Admire project comes into play that has just finished. So the issue with ad hoc file system is that there is no transparency. So users need to deploy their own ad hoc file system, they need to move the data between the namespaces, and you have the data actually stored at two places, right? And the Euro HPC Admire project, it is about adaptive multi-tier data management. largely speaking about improving the job pipeline that exists in the job scheduler. So for instance, if you have at some point some nodes that are idle, you could expand an application and the MPI process to that node as well. So this is what we call a computational malleability, but there's also I/O malleability, where you just increase and decrease how big an ad hoc storage system is, independent on the application even. So there was also a big focus on the ad hoc storage system, and here next I will talk about, well, how we can make ad hoc storage system more usable and transparent. And this is where GeckoFS Lustre integration with HSM comes into play, which is in the project Mainz and DDM Collab. So JGU is Johannes Gutenberg University Mainz, where I've worked before. And then we have IO trace analysis, and then how that later plays into just-in-time staging. So basically that means, in principle, you could move data into an ad hoc storage system right when the application needs it, and you can stage it out when they no longer need the output. So we were at that point. Users need to start their own file system, right? So this is now red line because it's actually not good. And instead in the project, what is happening is that we have different components now as well. So we have the IO orchestrator that is called SCORT, that is developed in the Barcelona Supercomputer Center, which is an additional component and basically just manages all these GeckoFS instances or any other ad hoc file system. And then there's an additional component which is called Cargo, which manages the data staging. This is basically an MPI application to have parallel copying between namespaces, but there's also quality of service in there and direct bindings to GeckoFS. And these are both developed by Barcelona. So then you see there's an additional one here between Slurm, because there are now additional Slurm arguments that were also developed in the Mire, where basically users just say, well, I want an ad hoc storage system, and I have this input path and this output path, and then the Mire framework is doing the rest. Now the issue here is we still have two namespaces, right? So we still need to define input-output, and ideally we would want to have that in the same namespace. And this is where the HSM component in Lustre comes into play. Of course, HSM tiered storage is typically used for archiving. This is where it comes from. And at its core, the file data can exist somewhere else, and the metadata still resides in Lustre. And then when someone accesses a file that is currently in HSM, it triggers a flashback so that users can actually use it, read it. And then we have in the middle the copy tool that moves the data back and forth. So this could also go the other way around. You could use also node local storage, and this is what the persistent client cache is. So it's in a sense similar here, but it's not a distributed namespace what ad hoc storage systems have. So we have two caching modes in Lustre PCC, which is read-write, but this is only for a single client. If two nodes are accessing the same file, this is not allowed, and then it's flushed back to Lustre, and then you have Lustre global performance again. And the other one is read-only. This works for multiple clients, but because it's not a global namespace, you would need to copy the data multiple times. And the idea is here to combine HSM with such an ad hoc storage system, so you don't have these drawbacks. So when we look again at that figure, we have now an additional point here. So in our team, we have developed an HSM extension that basically only uses the HSM API to register a new HSM component, and then we would handle the archiving and restore commands accordingly, and this would then go between GeckoFS and the parallel file system, and it implements all else that HSM needs, right? So we have some preliminary experiments. There's here a quick note. This is on the Mainz Lustre file system, but not the main production file system. This is actually a small test Lustre. There's only 2 OSTs, so there's not a huge performance, of course. This is because we need some super user permissions to register a new HSM. But this is just to show that it works in principle. So we have here just a simple IO workload with 2 modes, either working on a single shared file or as a file per process. And because we have a distributed namespace in GeckoFS, there does not need to be any flashback if they're operating on a single shared file, whereas that would happen in PCC. And so the performance, of course, goes up the more nodes you have. If the application would work on a file per process basis, well, there's no conflicting access, and PCC basically has the same performance as GeckoFS because they're just working on the one node local SSD that is there. So in terms of applications, again, this is work in progress, so there's still some preliminary results, but this is also that it works for an application. We have NEC 5000. This is a turbulent flow simulation, which is a bulk synchronous application, a typical HPC one. And what it does is basically it just has however many compute steps you want. And then at every write output step, it would create a 700 megabyte file, but this is a single shared file. Right? So this is advantageous for us. And then the output file is generated every 5 steps, but what the users of NEC 5000 told me is that basically they want to have it every step, but this generates so much load that it's usually not possible on a production system because other users, of course, are also using that. But we could, in principle, also do that. And we see here just a little bit of a performance improvement. Again, these are just a couple of nodes because this test cluster is small, but it's about 20 to 25%. In this case, again, different workload would have another kind of performance profile. So this is the part for HSM. Now, when we have the staging, we want ideally to not stage the data at the output data at the end, but also already while the application is running. And so the question was, well, when do we actually stage out the data? And we've already talked about bulk synchronous application that seems to have periods of I/O and computational phases. And this is where the I/O trace initiative comes into play. So this is a Minds-led cross-project initiative where collaborations were also with DDN, CEA, Madrid, Argonne National Labs, Lawrence Berkeley National Labs, and it is basically an ongoing community effort to improve knowledge about how HPC applications actually work. And it is, you can submit trace files here, you can archive them, search them, compare them, and analyze them. You also get visualized what they're actually doing. So we now, so this website has more than 40 traces already from different domains, molecular dynamics, deep learning, and also traditional HPC applications, with also up to 130K rank runs. So this website was deployed at the end of last year and will still be continued to be supported after the project ends. So the whole thing is built on Darshan profiles because Darshan profiles are already available in many sites, or at least Darshan. And it offers interactive heat maps and also Trishti integration. This is from Lawrence Berkeley for I/O recommendations. So, and this is the website, but more importantly, we have full DOI support. So that means all traces get a Zenodo link and are, well, you can reference them in publications and a website, and they will stay there. So just 2 quick examples, because there are a lot of metrics on this website, but I have here 2 examples. One is Wacom++, which is a water community model. This is just a small one here, but it shows that we have little bursts every now and then, and it's periodic. Basically, we have computational phases and I/O phases, and here's also distributed deep learning application with Horowat, where we would see, well, in the beginning something is happening and then only few ranks are operating, then all of them are working on I/O. And this whole thing would be interactive. You can look at them with your mouse, you can check what is read, what is write, change the logarithmic, and so on. So if you want to contribute there, if you have Darshan profiles, feel free to get into contact with the Minds team so that it gets continuously filled with more I/O traces. So we've seen that a lot of bulk synchronous applications have this computational and I/O phases. And so this is where we joined forces with the university in Darmstadt in Germany. And this is where frequency techniques for I/O come into play. So this is a tool called FTIO that was published at the end of last year at IPTPS. It's also available on GitHub. We get the links later. But the idea is here that we examine the I/O behavior in the frequency domain, right? And these one describe then the temporal behavior in a single metric, the period, whereas the period is just a time between the start of consecutive I/O phases. And the idea why we did that is, well, you could, in principle, only stage out data while a computational phase is running, and don't stage while the I/O phase is running, because in the I/O phase, the ad hoc storage system is also used. And so there are different ways of doing that. We have the online and offline mode. Online is the most interesting to us, so we could feed it this information, and then we get predictions when is the next I/O phase or computational phase going to happen. So in a nutshell, how that would work is we have, your compute job, you get I/O requests that go into a trace file. In this case, this is offline characterization, and it goes into this FDIO component where the signal is discretized. We go into discrete Fourier transform, get rid of the outliers, right? And in the end, we get a frequency out of it. So we get this cosine wave here that gets the frequency and also the period, how long the I/O phases are, and the average bytes per phase over time here. Right. So this is interesting, but it's offline. But for online, we can do the same thing, in which we would send this I/O information during runtime. And this is happening from the GeckoFS clients. Per rank is sending the current I/O to FDIO to get the predictions for the next period during execution with the frequency interval and also the confidence, right? And we only want to stage it when the confidence is high. So there's a whole paper about it at IPDPS, but this is also available on GitHub, and Ahmad Taraf, who was main authoring that paper, he has also a nice talk on YouTube if you want to learn more about it, because he knows a lot more about this than I do. But this is what we then use, and we worked also with the University in Darmstadt for that, and to basically put everything together, right? So first, let's look into GeckoFS Cargo and FDIO. So we have now an additional component here, and we send the periodic I/O rank metrics to FDIO that generates the frequencies and when computational I/O phases are happening. And then when a computational phase is happening, or it believes that it will happen soon, it will send a stage out trigger to Cargo to move data out. Right? So we're effectively overlapping copying data out of GeckoFS into Lustre while the application is running. And so this is also some preliminary results, this time on the main cluster in Mainz. Again, NextFS 1000, same workload. And what we have here is we have the four leftmost one is with FDIO. The other one would be you do the application and you stage out after. So you have a little bit more time that you need to stage out that information. And the important part here is that we seemingly have very little, well, over it here, but this still needs to be investigated. So the application isn't impacted as much, but the stage out time is much lower. Right? But again, the next steps here, there still need to be larger scales, more applications, and also comparison with the PFS. Because, of course, this only makes sense to use if it's all faster than if you would work on Lustre itself. Right? But again, this depends on the workload that we're having. So this is the full proposed architecture, to summarize, basically. So the user no longer has to do that much. They basically only ask for, I want an ad hoc storage system and the typical application and job. Then the Admire framework with Scort and Cargo are kind of doing the rest to manage the GeckoFS system and how it's deployed. Input data is staged into the ad hoc storage system. And then we have the additional component FDIO that is getting the per rank metrics from the ad hoc storage system to trigger more intelligently when data needs to be staged out. And in addition, and this is something that still is pending because we have currently Cargo, FDIO, GeckoFS separate to Cargo and HSM, but in principle they can go together. So, to conclude, GeckoFS can provide I/O advantages, and we have seen them. GeckoFS is an I/O 500, and it went quite well in our first way around. But in their basic form, users still have to do a lot, and this doesn't make them very useful in the grand scheme of things. So what we need here to make them work and to make applications faster and to get less load onto the parallel file system is to have transparent deployment and staging, integrate the ad hoc file systems with Lustre HSM mechanisms so that it's all in a more or less single namespace, not single namespace, but same path, and then predict I/O phases to have intelligent data staging. Next, finalize the whole thing with large-scale experiments, and here are all the resources again. The I/O Trace Initiative, again, if you want to contribute, feel free to get in contact with the team in Mainz. GeckoFest in Barcelona as well. We have FTIO, SCORT, and Cargo. That's it. Thank you.
Cool presentation, Marc. Question. This combination GeckoFS and Lustre, is that meant to be basically in main production at Mare Nostrum?
No, at the moment it's
an experimental.
It's just an experimental thing. Yeah.
Right, that's my understanding. But is it meant at one point to become, let's say, the standard production environment?
Well, I can't speak for Mainz at the moment, if they want to integrate it and have that. If it works, why not? But again, it's still in the early stages. There are a lot of things that we still consider. There are a few, consistency challenges that still need to be dealt with. There are tiny, places where consistency can become an issue. But I mean, in the end, it's possible because it's just an application that uses the HSM API. Okay. But it's not planned at the moment.
Yeah. Good. Thank you.
Other question? Yeah. So you consider the load on the GeckoFS, before you're staging out. Do you consider the load on the parallel file system as well to see when it's time to stage out, or not at all?
Not at the moment, but these are metrics that, if I remember correctly, were collected in the Admire project, so they would be available, yes, but we don't consider them at the moment, no. At the moment, the general idea was, well, if everyone would do that, then the load of the parallel file system would be much better in any case.
It can't be worse than what it was doing before.
Yes, exactly.
So I have one question regarding the I/O Trace initiative. The tools that you are using to provide the traces, the heat map, what is the right needed to the users to do that?
Okay. So you would need Darshan greater version 3.4 because this is when this information was introduced. Basically, heat map is a middle ground between just collecting counters, I/O counters, and full-fledged tracing. But in the end, you can either compile it as a user, compile it directly when you compile the application, or use LD preload to get that information out, and that's it. And there's also not much overhead. So no special permissions are needed. Any user can submit if they want. Okay.
So you don't need any admin stuff to do that? Okay. And the idea behind that is to rank the different codes to know which one is production ready or not, because you have some codes that do some stuff which is not really good for file systems, for parallel file systems, and we need to know that before they can go in production. So it's really interesting for us.
Yeah, I think this would be a great way to just look into that. You get the results more or less immediately. And again, currently, as I understood it, the goal is that this one will be also supported in the future, because these things popped up every now and again in the past, but if they're not continually supported, it makes no sense. But at the same time, it only makes sense if people contribute. So, yes.